Well, so let's take a look at chapter 10. Let's do a quick overview. So we're going to concentrate on the first few sections of chapter 10, moment of inertia for areas, parallel access theorem, the moments of inertia for composite areas. 10.3 is really just it's a moment of gyration, which is a special calculation that's used for designing columns, which you might get involved with someday. Won't spend too much time on that. And then mass moment of inertia. So essentially what we are looking at when we look at the mass moment of inertia for areas is we're looking at how likely a beam is to bend. So in this particular example, you've got three beams, A, B, and C, and you've got the test set up there on the far right-hand side, right? There's a pressure being put down, and we're going to see how quickly they bend. But of course, A is an I-beam, so hopefully you'd recognize that an I-beam is unlikely to bend, very unlikely to bend. So that of the three, that's the one that's going to be able to accept the most pressure before it bends. If we look at the one in the middle, B, B is essentially a piece of dimensional lumber. Think of 2x4, 2x6, 2x8 up on its side. That is stronger that way. So if you went, when I lived in Connecticut, if you went and walked into my cellar of my house, you'd see floor joists in the house set up that way because it's stronger for dimensional lumber. Not as strong as an I-beam, but it's the stronger way to put dimensional lumber. They're less likely to bend. There are, of course, limitations of load and spans, but that would be the stronger way to do it. And of course, C is taking your dimensional lumber and laying it down. So hopefully you'd recognize, right, essentially that's a diving board, right? A diving board is going to deflect all over the place. So if you were building a house, right, your I-beams are for your heavy structures. Your B would be for your floor joists or for ceiling joists, right? And C, you don't use that when you're building, unless you're going to be building a diving board. In this case, again, mass moment of inertia determines how likely these things are to, that's what we're going to be finding out, how likely they are to bend. So there's two ways you can do mass moment of inertia for an area. One is with integration, which is being laid out here. The second is if you have standard shapes, right? In this particular case, you've got a blob. So the blob in this case is we're going to define an area, use that to find the area of it, and then we're going to determine how likely that is to deflect around any of the axes. In this particular case, right, you've got the x-axis and the y-axis. When we have the standard shapes, the back page of your textbook is going to be the thing that's going to be really handy, right? The back page of your textbooks for chapter 9, so centroids for common shapes, and it also shows your moments of inertia for areas for common shapes. It's going to be very similar to the process that you saw that we did for finding the centroid, right? We're going to find a strip, and we're going to define that strip as by its width and by its area. So in this case, the dA is the area of the strip, right? You can see here it's y tall and it's dx wide, right? You can do a horizontal or a vertical strip, just like before. So you'll see that there's a few suggestions as you go through the slides of which one to use. And again, very similar to like the centroids. So second step, of course, is to find your mass moment of inertia. So for the y-axis, it's going to be x squared times dA. And for the x-axis, it's going to be d times ix. For this figure up here that we were doing this example for because of the direction that we picked the strip in. So parallel access theorem allows us to find a moment of inertia through a axis or through it. So let me step back for a second. So we have we know a moment of inertia. These tips could always trip you up every semester. So we know a moment of inertia around a particular axis. What we can do is we can find that from the parallel axis theorem. We can find that same, because of that area going through that axis, we could find it through a parallel axis. And that's what the parallel axis theorem allows us to do. Very handy when we get to the tables, which you'll see in a little bit. We'll do some problems, of course. Radius of gyration, of course, as I mentioned, is essentially something that you use for designing columns, kind of a plug and chug type thing. And again, we're not going to spend a lot of time in this chapter. Actually, I don't think I gave any homework problems on this, and there'll be no quiz or exam problems on the radius of gyration. Moment of inertia for a composite area. So just like with centroids, when we have known shapes, right, we can do the same sort of process. We build a table with the known shapes, right? So in this particular example, what we actually have is we got a big rectangle, the blue one and the white one, right? We can subtract the white one from the blue one, and we got a couple of triangles up on top. So we can make a table and then use that table based upon the shapes and based upon the back of your book to sum together and to get a mass moment of inertia for an area of known shapes. So how do you do this? You divide it into its known shapes, again, just like a centroid, right? So in this particular example, right, there's a square with a hole cut in it. So what do we have? We've got a square, and we're going to, actually a rectangle. We got a rectangle, and we're going to subtract out the hole, right? Because a hole is the same thing as the circle, subtracting it away. You're going to locate the centroid for each of these, and you're going to look at the perpendicular distance from each centroid to the desired reference axis. So you see in this particular case, the centroids for both of them are going to be in the same spot, right? Rectangles in the middle, circles in the middle, right? And you can see that distance, that red distance there from the x-axis, which happens to be the thing the box is sitting on. So we're going to determine the mass moment of inertia for each of these simpler shapes. So we're going to do that. And we are going to determine the algebraic sum from those that we obtained in step 3. And we're going to do that by plugging those into the table, just like we did for the centroid. So there you go. There's a quick overview of chapter 10.